Hello everyone, I'm Jinjin Yan. I'm currently a PhD candidate at the University of New South Wales. I started my PhD at the Delft University of Technology in October 2016 and moved to the UNSW in March of 2018. Recently, I have submitted my PhD thesis. I'm going to present a piece of my research, two new pedestrian navigation path options based on a semi-indoor space. This research is one of the topics of my PhD. This presentation consists of 5 parts as shown on the slides. I guess all of us are using navigation applications in everyday life, either for vehicle or for pedestrian. In our previous research, we have classified spaces into 4 types. Besides the well-known indoor and outdoor, we introduced semi-indoor and semi-outdoor. This paper focuses on semi-indoor spaces. Such kind of spaces can be seen very often. They are physically enclosed from above and open from the surroundings. On this slide, you can see several examples of such spaces. Current navigation systems do not treat such spaces differently. However, some indoor spaces can enrich the navigation path options because they can provide shelters and help pedestrians to escape from rain or strong sun. Therefore, we proposed two novel path options, which make use of semi-indoor spaces. The most top-covered path, MTC path, and the path to the nearest semi-indoor spaces from departure, NSI path. The purpose of the first type of path is to guide the pedestrian go through semi-indoor spaces as many as possible. The second path type selects the closed semi-indoor space as the temporary destination. The two navigation paths are computed based on a navigation network, but the network has to be created from the spaces. In my research, I have used the Poincare duality to automatically obtain the network from the spaces. This slide illustrates the Poincare principle. Each space is abstracted by a node and the face sharing by the two spaces provides the edge. However, in navigation, not all adjacent spaces should be connected with straight edges. On the right side, you can see different implementation cases. Case A is the most common case. The semantics of the spaces is used to establish the edge, room to door to room. Case B and C illustrate cases when door is not available. In the two cases, additional step is needed to ensure that the edge does not go outside of the space. In our research, we consider all the spaces that are sharing face like the two spaces in case A are connected. Then, they can be used for navigation network creation, see figure D. But the spaces in case B and C are considered disconnected. To be able to deal with the semi-indoor spaces, we introduce 5 parameters as given on the slide. One parameter estimates the distance between two adjacent spaces. 2 parameters deal with the weights on the edges. 1 parameter evaluates the distance formed by semi-indoor spaces, and 1 for the percentage of top coverage ratio. Furthermore, 4 more parameters are defined for navigation paths. They take into account the overpass length, covered and uncovered length of a path, top coverage ratio of a path, and weight based on path length. This weight-based path length can directly reflect the attractiveness of the path. The smaller this length, the more attractiveness for pedestrian. Then, the two paths are computed following the steps as shown on this slide. In the MTC path planning, the criteria for minimization is the distance and the top coverage ratio. In the NSI path planning, the time is an acceptable time period of pedestrian to move to the nearest semi-indoor space. while the searching angle helps to reduce the search area. As it can be realized, there are three different path options for pedestrian. The new proposed path may not be the shortest path. To help a pedestrian to choose one, we proposed a path selection strategy. It works according to three conditions. The decision tree helps to conclude on a path. For example, if uncovered length of the MTC path is shorter than that of the shortest path, and the top coverage ratio of the MTC path is larger than that of the shortest path, then the MTC path will be recommended. So does the NSI path and the shortest path. To demonstrate the proposed theories, we illustrated them with 8 spaces, in which C, F, and G are 3 semi-indoor spaces. Figure B and C show how the network is created from the spaces. Figure D illustrates the distances between the spaces, which are used for computing original weights. Based on the original distances, for every 2 connected spaces, all the parameters are computed. Black dots are the nodes of the network. Red dots are the vertices of the curved edge to keep the edge within the spaces. The slide illustrates the values of the parameters in our case. For example, between the space A and F, the slide shows how the original weight, covered and uncovered distance, top coverage ratio, as well as the modified weights are computed. Then, for this example, 3 navigation paths are computed, path 1, 2, and 3. They have different path lengths, top coverage ratio, uncovered and covered distance, and weight-based length. Path 1 can be regarded as a traditional shortest path, path 2 as the most top-covered path, and path 3 is the path to the nearest semi-indoor space. To show how parameters of the path are computed, the path 2 is used as an example. Path length is a sum of the distances of all spaces in the path. Covered and uncovered lengths of the path are computed based on the distance offered by semi-indoor and other types of spaces separately. Then, top coverage ratio and weight-based length of this path are computed. Overall, with the decreasing of the coefficient, the weight-based length of the shortest path is rising, while that of the MTC path and the NSI path are falling. It shows that having a departure and a destination, with paying more attention to the top coverage ratio of a path, the most top covered path and path to the nearest semi-indoor space becomes more attractive than the traditional shortest path. We implemented the proposed theories on part of the USW campus, in which the indoor part is a beam model. We reconstructed semi-indoor space, semi-outdoor, and outdoor spaces in the selected area. Using the 4 types of spaces together, the navigation network was extracted based on duality. Finally, we computed 2 navigation cases. In this slide, the departure location is A, destination is B. For comparison, OpenStreetMap and Google Maps are also used for path planning. The navigation paths computed by Google Maps and OpenStreetMap obviously show that this system tries to guide pedestrians to go along with the road. They don't have any information of the semi-indoor spaces. However, the results of our approach show that the most top-covered paths try to include as many semi-indoor spaces as possible. We got similar results for the cases from C to D. We can see that the OSM provides a path between buildings. Google Maps gives a path along the main street of the campus. The shortest path of our approach is almost similar to that from Google Maps. The MTC path is quite different, which goes through the semi-indoor spaces to increase its top coverage ratio. See the ellipse on the bottom right image. For the two cases, having the information for the path because uncovered length of the MTC path is shorter than that of the shortest path, and meanwhile, top coverage ratio of the MTC path is larger than that of the shortest path. Based on the path selection strategy, the MTC paths are recommended. Therefore, we didn't compute the path to the nearest semi-indoor spaces for the two cases. We compared our results with that from OpenStreetMap and Google Maps. It shows that other than the traditional shortest paths, our approach also can include and use semi-indoor spaces to successfully compute the most top-covered navigation paths and NSI paths from departure. In conclusion, this research brings two contributions to navigation path planning. Semi-indoor spaces are included as in the navigation path as destination or departure. Secondly, MTC paths and NSI paths are two novel path options for pedestrians who need a navigation path with as many covers as possible from the top. In the future, we are going to extend this research to new pedestrian path options with semi-indoor spaces to indoor spaces, even semi-outdoor spaces or outdoor spaces for other navigation preferences. Secondly, investigate more aspects that are related to semi-indoor spaces, such as setting the threshold of top closure. Thirdly, investigate the preferences of users, which would have a higher impact on their decision compared to time or distance-based routes that are currently in use. Thanks for your time and attention. Any questions?